Our next talk this afternoon is by Boris Tsygan. Hope I got that right. Northwestern University. Operations on cyclic complexes, the Getzler Gauss-Manin connection, and non-commutative crystalline cohomology.
Thank you very much. As I said, I'm very happy to be here. Thanks for this opportunity. And so, well, it says Hodge theory and related topics, and I would say it's part of non-commutative Hodge theory. Yeah. And I hope I will give enough, background and motivations. But let me start by saying that if you have if I have an associative algebra over some scalars k, and maybe it's important for the context, and a differential graded or DG associative algebra, commutative or not, then there are standard constructions and the first of them is the Hochschild complex, Hochschild homological complex. For example, its lowest term is this, and it's the standard construction computing kind of self-intersection of the diagonal. It computes these Tor functors, which are also known as Hochschild homology. And then it can be extended in such a way, or it can be deformed like this. So U is a formal parameter, and it's some explicit differential like this. And maybe one thing to keep in mind is that it's pure linear algebra. It's independent of multiplication. It's some simple tensor construction which involves averaging over the cyclic group, and that's why we have the name cyclic for it. And here he is. Here it is. There is an explicit formula. Maybe I should say that in the lowest term, it goes like that, if you want at least some kind of concrete reference. And then there are also, there are also different versions of that. One could also take non-positive powers of U, and then one can take all of them and in all three cases the differential is little b plus u times big B. Okay. Now, where is the geometric and indeed Hodge theoretical motivation for that? When K is commutative and when A is commutative and Q is of characteristic 0, here we can have and similar format here. And the differential will be instead of B there will be nothing, and instead of capital B there will be the de Rham differential, and this is an explicit map which I may write down here. Here it is, and it so the claim is that intertwines little b with 0 and big B with de Rham. And again, maybe if you recall this formula, yes, it's okay. So yes, it is commutative at least, you know. In here, and when A is regular commutative, it's a quasi-isomorphism. And it's the theorem and also, I think, the map of Hochschild, Constant, Rosenberg. Of about 1963. And you see, so here with this differential, it is indeed filtration by powers of U is the Hodge filtration or some minor variation on it. Now, I'm not even sure if I will come to it, but maybe worth mentioning here that for differential graded coalgebras B, you also have you have dual picture. Now it will be co-chain complexes. I mean, very roughly speaking, it's like, let's say B is dual of an associative algebra, and you just take this chain complex and take its linear dual. But of course, when things are not finite dimensional, you may have problems, but it's clear how to do it. So just dual construction, and this Roman 2 refers to some technicality. You know, roughly speaking, I don't know. Something like that, you know, it's a doubly graded thing, and you have to take product. So but our definition of Hochschild complexes of coalgebras will involve direct sum and not direct product. So literally speaking, it's not dual to this one, it's something different. And there are reasons for that. Maybe when I come to it, I will say a little bit more. So far, it's just an aside. Okay.
What is an example of algebra which things that you claim? The verb. What is the example which you think of?
The main example that I will use is of any associative algebra A. Yes.
Dualizing it. No, it's not bad.
I mean, well, let's see. For example, maybe the good thing about quasi-isomorphism of differential graded algebras implies a quasi-isomorphism of their Hochschild complexes. So dually, and again, maybe let me stress that I'm doing with coalgebras. Now, this is not what I want. Maybe let me, and since I'm using it for the future, maybe let me tell you what it is. It's So it will be just so it's the standard bar construction. So for example here, and the co-multiplication will be just, you know, cutting the word in two. So for example, it's a cyclic or contractible when one is in A. So I don't want that, but fortunately, you know, the thing that I use is not homotopy invariant, which is usually kind of bad, but for me it will be good.
So it does not happen because it does not happen, or because one cannot prove that it happens?
No, it definitely does not happen. Yeah, and again, I will have an example later. Yeah, well, since I'm at it, why wouldn't I? And I think, well, Quillen proved it. John Jones, I think, proved something similar, and also Boris Tsygan and me. It was all, I think, around, I would say, 86. Yeah, maybe let me say a word. I recalled recently because somebody was at the conference last week, somebody was mentioning or referring to Drinfield's work from '86 on quantum groups. And I remember that in '86 there was this conference in Kyiv, Ukraine, and Drinfield came from Kharkiv, Ukraine, and it was a beautiful, beautiful May day. And I remember how, you know, we were walking after Drinfield's talk. And well, it's so sad that this madness is happening, and I hope it will be, I hope it will end soon. Drinfield, well, never mind, okay. So, yeah, the theorem is this, that if you want to compute Hochschild homology of A, it will be so Hochschild is kind of self-dual, you know, self-Koszul dual. And if you want to compute negative cyclic of A, it will be usual cyclic non-negative of the second kind of. And if you have periodic, you have periodic. So there is this self-duality property, and I will tell you in a little bit why is it important, but maybe let me first introduce another key component, which is the differential graded Lie algebra of Hochschild cochains. So what is this? It is multilinear maps from A to itself, and it has a differential, and also it has a bracket. Which again, around 63, was introduced by Gerstenhaber. And a good interpretation is that, or maybe rather, let me first introduce the notation. It's a bracket of cohomological degree -1. So this is my differential graded algebra, and so in particular, G0 are just endomorphisms, and the bracket are just, composition. Now, cocycles are derivations of A, so infinitesimal symmetries if you want, and coboundaries are inner derivations. Okay, so again, maybe since cyclic chains are non-commutative forms and Hochschild chains, then maybe this too carries some geometric meaning, and we see that in degree 0 we kind of recover vector fields. So again, let us say that we are in characteristic 0, then algebraic then there is an explicit way of linking the two, where this, by definition, it's just this formula. You have n vector fields, so yes, you can, apply it to n functions, and you just average over the symmetric group. And again, it intertwines 0 with delta and is a quasi-isomorphism when A is regular, I think Noetherian probably has nothing to do with this, but since we are taking duals, whatever, maybe let's say Noetherian. Oh, in characteristic 0, of course. Now, quite a bit of HKR can be, something could be said over Z or in positive characteristic, but not all. And in positive characteristic, it becomes an interesting thing. I mean, it's interesting also. Okay, now maybe how about does it intertwine the Gerstenhaber bracket, and here one defines this Houghton bracket. Important for, Poisson geometry and Hamiltonian mechanics, and Hamiltonian Houghton bracket on multi-vector fields. Does it intertwine them? And the simple answer is yes. On cohomology, so you have, again, maybe I should say delta is equal to 0, so you have a complex whose cohomology is itself, and there you have the cohomology there, and it's an isomorphism on cohomology, and yes, it's an isomorphism of Lie algebras. It's a simple fact. And the second answer is also yes, but it's a much, much more difficult theorem. Again, in the regular case, as proven by Concevic in 97, the formality theorem identifies, makes equivalent those two differential graded Lie algebras, which is a much, much stronger fact. So DGLA of Hochschild-Cochains of a regular algebraic variety in characteristic 0 is formal. Okay. A good interpretation of the Lie algebra, DG Lie algebra of Hochschild-Cochains, is that it's co-derivations of the bar construction, because it's kind of same energy, as they say now. It's like dually, if you want a derivation of something free, you only need to define it on the free generators in whatever way you want. And it's a dual thing if you want to define a for derivation, you only need to know its projection to A. And okay, and from here, so take the universal enveloping algebra. Then treat it as a coalgebra and compute the cyclic cohomology, which is dual to cyclic homology. And then you still have multiplication, and so this multiplication induces a multiplication here. We need some little information about, CC is not just some functor, it's a monoidal functor. It's, it does respect a product of algebras, coalgebras. So, and what we get from here is that so you get that, well, to any associative algebra A, we associate a Lie, GG Lie algebra G of A, and to any Lie algebra or any actually bialgebra, we associate this infinite algebra. And the result, because of this theorem from the 80s, the result is that it serves as a kind of big enough algebra of symmetries over the negative cyclic complex of my algebra. Maybe I should see that for that the symmetries, the universal enveloping algebra is a subalgebra. So in particular, And it's an explicit formula. So, for example, the relations, of course, act on tensor powers, but maybe importantly, another thing that I need is that maybe let me put any any binary multiplication on my algebra A, we see that it lies in C2 of AA, and well, modulo 2 torsion so should I, well, it's some other multiplication, maybe not our multiplication in my algebra. And well, modulo 2 torsion, the element commutes with itself if and only if it defines an associative product. So in particular, there is this remarkable element there is this particular self-commuting element in the algebra of Hochschild cochains, and both chain and cochain differentials, they could be understood as the bracket with and the action of this particular element. Okay, now this can be computed. And again, maybe the reference, I don't know other reference except the book we are writing. That we are writing, that's in progress, and that I have the file on my webpage. I can give you a better reference. It can be computed, and actually, well, or for any and well, probably I need to spend a couple of minutes here, maybe.
Or you had the universal development.
Oh yeah, that's it. Yeah. Probably I need a couple of minutes, maybe not. So first of all, I mean just the universal enveloping algebra of G. And then this is the augmentation ideal. Yeah, and this is a notation. And also U, which is central in everything. So this is, there are no, yes, and another relation is of course that it's kind of, whatever it is, it's G covariant or invariant. And then the differential. And here it is. So there are three components, and two are kind of obvious. One comes from the differential, inherent, I mean, present in the differential graded Lie algebra G. The other is the co-bar differential. It's the dual of this bar construction that I described. And this is a new one, which is very much related to capital B, to the dual. It just drops the parentheses here, so it kicks it back to the universal enveloping algebra. Okay, therefore, I call it U of G semi-direct product with co-bar So it's a very, very explicit thing. And from here, we can deduce the following, that so whatever I called it, yeah, I have to invert U, and well, it will be of total degree 1. There will be this specific element which will satisfy which will satisfy this. And maybe just say it's kind of instructive, but what I need from it is just, and here I have something, some polynomials in R, and here I have those other generators, the cobar generators. Yes, and last but not least, u to the power negative n and divided by n factorial. Some explicit construction with very much, with a very strong d-module connotation that I have not, well, I don't understand them, but I think it's very thought-provoking. Especially, this d-module kind of formula, it is used in Hodge theory, mixed Hodge modules, and
We're just on the algebra. What is this X bar?
I can write you an explicit. I mean, it's absolutely explicit.
No, I know, but what is meaning geometrically?
Oh, I have no. I mean, what it means geometrically,
Yes,
I have
this
no idea.
Equation is telling you something.
There is a differential equation, kind of a difference equation, and I mean, I can write a formula later, and it will be really. It's like direct image and f to the s. This Bernstein-Sato polynomial, but yeah, but that's maybe separately. But so what's important to me? Two things. First of all, maybe if R is divisible by P, it makes sense periodically. It will be, you will not have any denominators, but because P to the n over n factorial, you can, it goes to 0 periodically when P is greater than 2. Okay, so now let me just, hopefully 2 minutes will be enough. So theorem number 1. Given scheme S and then OS algebra A. And let us say and this is the product, kind of point-dependent product. So it lies in, or should I say, Hochschild 2, or maybe you have a family of algebras, therefore a family of Hochschild complexes of Lie algebras. So you have an element like this. And also, yes, and of total degree, I think 2. Correct? 1 plus 1 and 0 plus 0. Now, apply, yeah, so start with you have a family of complexes, or maybe you view this, yeah, 1 more minute and I'm done. You view this as an algebra over OC and use the tensor products over OC. So you have a family of complexes, and then you have this, but you, I mean, this is not a flat thing, but this is how you flatten it by adding this term. So you get, well, this Getzler's Gauss-Manin superconnection. So if we believe that periodic cyclic chains are like non-commutative de Rham complexes, so you have this superconnection on the bundle of non-commutative de Rham complexes. Okay, well, let me stop here. Thank you very much.
To thank the speaker, and are there further questions, comments? If not, we have a short break. The next talk is at 4:15.